Donovan Buck is here to talk to us about robots.
Yes. Sorry about the delay, everyone. So specifically, my talk is about Johnny 5 and some of the ways that it has grown over the past couple of years. It's really opened up a lot of new possibilities in JavaScript. We've moved way beyond blinking and LED. The first time I saw Johnny 5 was in Portland when Rick Waldron presented at NodeConf in 2012, and I was really impressed. I thought that's really cool, and I would love to be able to do something like that. So I went to NodeBots Day in Austin in 2013, and I learned that it actually is pretty easy, and it's very inviting, and it's a fun thing to do. So I was hooked, and I decided to build a robot, but I don't do things easy. I decided to do something kind of impractical. I wanted to build a walking robot. But I learned early on that walking is hard. It's really, really hard. It's very impressive that we all got in here today without falling down. There's a couple challenges that have to be overcome. First, the robot has to maintain its balance. And there's two kinds of gates you can use to do this. There's dynamic gates and static gates. Most of these are dynamic gates. Static gates are those where the center of gravity is always contained within a polygon that's defined by the end effectors, the feet that are in touch with the ground. And I knew it was going to be hard to talk over this. If at any point the center of gravity, or if at any point the robot walks or stops during its walking gait, it will just stay upright. That center of gravity is safe. It's still within that polygon. With a dynamic gate, the opposite is true. There are some points in the gate where if it just stopped moving, it would fall over because it's depending on inertia, or it's just getting another end effector out there before it falls over and hits the ground. So static gates are easier, and I decided to build a robot with static gates. And I decided to build a robot with... That's my favorite one. He just looks like I quit. So I decided to build a robot with a static gate, and I decided to go for 6 legs because I thought, well, that'll be easier. You've got all these things in contact with the ground. It's less likely to fall over. We're almost done. Yeah, we're done. We've gone through the whole loop. So if you want to see this again, just find me later. So for the second challenge, we've got to talk a little bit about some robot anatomy. This is one of the legs on my robot here. It has 3 servos. It has a coxa servo, which moves the whole leg assembly in this direction. It's got a femur servo, which moves everything this way. And then it's got a tibia servo, which moves everything this way. And the other important part to note is that end effector. That's the part that comes in contact with the ground. So here's that same assembly from overhead, coxa, femur, tibia. And I thought that to make this robot walk, all I was going to have to do is put the end effector in contact with the ground and move the coxa. But I was wrong. It gives you a drunk robot. It's very sloppy drunk, too. What happens is you've got a couple end effectors on the ground, and they're both turning. And they're both pushing in on the robot. They're working against each other. One of them's got to give. It's going to slip and slide all over the table or whatever surface it's walking on. It just doesn't look good. We want the end effector to move in a straight line that's parallel to the direction that our robot's moving in. And to do that, we've got to move all 3 joints in concert. So we move the coxa, we've got to bring that tibia in to keep it in a straight line. But when we bring the tibia in, the end effector moves up and down relative to the ground. So we've got to lift the femur up and down. It's a lot of things that need to happen simultaneously. This robot has 6 legs. So that's 18 servos, all working together in concert constantly to keep this robot moving forward smoothly. So I wasn't sure that was even possible. So all the work's being done on the computer, and it's sending commands over USB to the Arduino that's on the robot. And I figured, this needs to work at about 30 frames per second to look smooth. That's 18 legs. That's 540 commands to the servos every second. I didn't know if it was possible. Fortunately, this guy, Rick Waldron, is the inventor of Johnny 5. Did a presentation at Empire Node in 2014 called Bits of NodeBots Next. And what he's got here, is it playing? Oh, good. It's not playing on mine. So what he's got going on here is a quadruped, which has legs very similar to mine. It has 3 servos on each leg. And it's moving using Johnny 5's built-in servo2 function. You can move a servo to a certain number of degrees. You can pass in a degree value and a number of milliseconds, and it will take that long to move the servo. And He's actually sending 1,200 commands per second over the serial port to the Arduino, and it's handling it just fine. You can actually see a little bit of the sloppy robot stuff here. Its feet are kind of sliding back and forth. But that's understandable because he had to write all this stuff himself, all his timing mechanisms. If you've ever used temporal, which is his replacement for set timeout, I think it was invented just for this robot. It was a lot of work to get the movement to happen here. So when I set out to do it, I wanted to make it easier for everybody, and I wrote the animation class for Johnny 5. It gives us some familiar metaphors for doing animation in the real world. It gives us a timeline, cue points and keyframes, tweening and easing functions. Courtney's talk from yesterday would be perfect to insert right here because everything she talked about applies to the physical world as well. We want to ease those movements of the joints so that it looks more natural and smooth. Now, I'm going to dive into some animation code real quick, but not with the intent of teaching animation. I just want to make a couple points. So this is animation, an animation creation. We're just going to require Johnny 5, instantiate a new board, and once we get the ready event, we're going to create a couple of servos. The first point I want to make is Johnny 5 is awesome. That's 4 lines of code. We've established communication with a microcontroller. We've set up PWM on 2 channels so we can control servos. And we can now send commands straight to those servos, servo.240, and it will move to 40 degrees. And to me, that's just amazing. 4 lines of code in JavaScript. So very accessible, very easy to get up and running. So moving on, we want to create a target, a set of things that we're going to animate. In this case, I've made those 2 servos, one called right, one called left, and I'm passing them in an array. So that's my target. And then I'm going to create a new animation. That gives us a timeline to work with. So we've got that timeline, and I've given it a target. I've told it its legs. Now I can in-queue an animation segment. An animation segment's like a movie clip. It's a short, reusable piece of motion that we can just drop on. That's got a lot of really helpful properties. We can give it a duration. This is 5,000 milliseconds, so it's a 5-second animation. We can give it an easing function. I used TJ Holloway-Chuck's Node Ease Component library. We can give it cue points. These are the points in time, percentage of completion, so we've got 25%, 50%, where we're going to have keyframes, where we're going to be setting values. And then I can give it a keyframe array. Now this is a 2-dimensional array. The first dimension maps to the elements, the devices that we're animating. The second dimension maps to the cue points. So that's pretty easy for doing a complex animation. But you do have to build this array. This keyframes array in particular can be kind of frustrating. This is a keyframes array from a walk segment, and it goes on for another 2,000 pixels. So that's, only a crazy person would engage in something like that. And it's also very prone to errors. Here's an early test with my robot. And that's what you get when you send infinity to your servos. I got really lucky in that these servos weren't completely assembled. The robot wasn't completely assembled, so these servos had a full range of motion. If I had done this later, that would have cost me hundreds of dollars because those servos would have stripped out. So that was a really bad way to do things. Fortunately, this guy stepped up, Ronald Jaramillo. He's out of Copenhagen. Does anyone know Ronald? No? If you ever meet him, give him a hug because what he did was awesome. He created an application called Go Johnny Go, which gives us a GUI interface for building servo animations in Johnny 5. I'm going to switch over to Go Johnny Go and do a little demo real quick because I think it's pretty awesome. There we go. And I probably want to mirror because this would be painful otherwise. Okay. So here are with Go Johnny Go. And we might want to put the camera on this so we can see better. So Go Johnny Go lets you create any number of projects. And you know what? I was wrong. We'll do it in a sec. and it saves them to your working directory, which is really nice wherever you've stored this application. You can define targets, your servos, and edit them. You can set there all the parameters that you'd be passing in Johnny 5. You've got a nice little form you can create, fill out, and it'll set the properties for your servo. I've got one here, a Cascadia demo. Let me see if I can make it fit. I cannot, so we'll have to scroll. So we've got our cue points. You can just click and drag them around. We've got our we've got keyframes. We can drag them up and down. I don't know if you can see the robot moving very well here, but we can set it up to move it up and down. So I can play this animation and see how it looks. So that's pretty pedestrian. I want to add some interest to that, so I'm going to go to this cue point, move that up, move that up. We'll rewind and play. So we've created a wave animation pretty easily, quickly and easily, and we can just click export, and it gives us that entire animation segment object that we can just paste into our code and work with. By the way, animation segments can be created dynamically. They don't have to be created in advance, so they can respond to environmental parameters, change the gait of the robot, things like that. So that's really cool. Ronald deserves a big round of applause because he made it a lot easier to do stuff in Johnny 5 with animation. So what kind of stuff can we create with that? Let me switch over. Okay. All right, so I'm using a Leap motion controller here to control this robot. This is a very narrow table. So let's get that walk going. Okay, so that's a typical walk motion. What's happening is we're moving 2 legs at a time. One leg comes up off the floor, and when it gets to its inflection point, we start moving a second leg. And when that leg gets to its inflection point, the first leg is down at the ground, and we start moving a third leg. So we've always got 2 legs off the ground. That helps. So we've always got 2 legs off the ground and moving forward. That's where we're moving those legs in a straight line. Now, turning has its own problems. Each leg is describing its own circle. And those circles have to be concentric around the center of rotation. So it just makes it a little more complicated to create a movement like that. So that's pretty cool. Let me get back to my presentation here. That's pretty cool. It lets us do some really complex things with Johnny 5 and animations. But, in a way, it's not very cool. We're telling every limb what to do in advance without regard to the robot's environment. We're explicitly setting the angle on each servo, which means we may not be putting our end effector where we really want it to be. We want our robot to respond to its environment, like I said. This is a fancy remote control toy now, and that's not what we want. We want robots that can be aware of their environment and respond to changing conditions and do the tasks that we give them in a smart way. And there's a lot of things that have to happen to get us to that point. We need to be able to map the environment that they're in more detail and at a much farther range. And we need to be able to do wayfinding. But first and foremost, we need to be able to position our end effectors in a way that's not predetermined. And we need to be able to tell the robot, hey, go push that button. So we're now dealing with points in 3D coordinate space instead of single degree angles, what we call joint coordinate space. We're going to be working with 3 tuples, x, y, and z coordinates. Animation handles that. We have the ability to tween between points in 3D coordinate space, complete with easing functions and all the other helpers that we have for one-dimensional values. But we still needed a way to position the end effectors. Fortunately, Raquel Velez works at NPM. She's a superhero. Her superpower is math. She demoed Manny the Manipulator at JSConf in 2013. And at Manny's heart was a module called Vector. It's a linear algebra module that has inverse kinematics solvers, or helpers for solvers, that's optimized for robots. Most linear algebra libraries are way more, massive overkill. This was perfect for doing robotics. And what inverse kinematics is, I'm going to talk about forward kinematics first. Here you can see Raquel's dragging a couple sliders, and those map to the degrees for these servo values. So what we're doing is we're looking at all the joints and the segments and finding those angles and lengths and figuring out where the end effector will be. And it's rendering where that end effector is on the left in the browser. With inverse kinematics, we do the opposite. We have a desired end effector position. You can see she's actually dragging the end effector here, and it's solving for those servo values. So we've got a way to solve inverse kinematic formulas. We've got tools to help us do that. But we still need a way to define kinematic chains. We've got a new module called THARP that works with Johnny 5. And THARP lets you define those kinematic chains and systems of chains or robots. And it takes an end effector position and segment lengths, and it'll spit out servo angles for you. So THARP code is incredibly simple for what it does. You just say, I want to create a new chain. You give it a chain type that's predefined. We've got a coxa whose axis of rotation is parallel to the y-axis in global coordinate space. And we've got a femur and a tibia that are both parallel with the z-axis in global coordinate space. You give it an origin relative to some focal point on the robot. I just use the robot center and bottom. You tell it the segment lengths. Oops. You give a start position for your end effectors, where you want your feet to be when this robot first turns on. You choose a constructor to use. In this case, we're using Johnny 5 servos, but you could use any constructor. You could be working with linear actuators. You could be working with some other device that I haven't seen yet to manipulate your robot's limbs. And then you pass in your ops objects for those devices that are going to be created. And this is just a standard Johnny 5 ops objects for each servo. So then you've got to create a robot. This is even easier. You tell it what kind of robot. It's a hexapod. You tell it what chains you've created, and you pass those in a certain order. We've got right one, left one, right two, so on. And now you've got everything you need for Johnny 5 to go and do the math, to calculate the coordinates for each of those servos, and put that end effector where you want it to be. So we're going to do one more demo. One more awkward toggle between screens. There we go. All right, let me turn it back on. All right, so the first thing that's going to happen is very similar to what happened with the last walk that we did. I'm going to open my hand and it's going to stand up, but there's something very different happening on the back end. Instead of explicitly defining the angle for each and every servo, we've only defined the position for the end effectors. So let's get that working. There we go. And now what it's doing, it's not moving at all. It's being told to keep its end effectors in a fixed position, but I want it to respond to input from the real world. So in this case, as I move my hand up and down, it's going to move up and down on that y-axis. I can also move it on the x-axis and the z. But I can also rotate around all those axes. And you can mix those movements. Remember earlier I said I was going for 30 frames per second? We've actually got this at around 60 frames per second. That includes all the math, sending all the signals over to the robot. So it's incredibly responsive, and it gives me a lot of hope for some of the incredible things we'll be able to accomplish in the future with Johnny 5. So we can probably turn it off now. Thank you. So, thanks. So next steps for THARP. We want to add more chain and robot types. Robots are expensive, so that might take a little while. But we want to get those in there. We can get a lot of people to put in pull requests when they buy their robots, and we'll help make THARP work with them. We also want to wrap a variety of gate styles into Tharp so that people can choose to not write their own gates, because that's a lot of work. And we're going to do it for each robot type. We want to have quadrupeds, hexapods, bipeds. Bipeds will be cool. Spider bots, you name it. So Johnny 5 is pretty amazing. It takes hard things and makes them really easy. And because it uses JavaScript, almost anyone can get up and running with robotics in an afternoon. And as developers, JavaScript developers, our range of influence is growing. What's expected from us will change. And unless you're going to be retiring soon, you'll have opportunities to build for other types of hardware and internet-connected devices if you haven't already. And spending time with NodeBots is fun, yes, but it can also pay off and get you prepared to work in that world. And last thing, if you have ever thought about contributing to open source, but didn't know if there was a project that needed you, or were just intimidated, I know I was, look at Johnny 5. We have 84 contributors now, and it's a pretty amazing group. They're very knowledgeable, overwhelmingly positive, and respectful to everyone who wants to get involved. So I recommend you check that out. So that's it. Thank you all very much.